The last of the three ways of energy transfer is radiation. And so electromagnetic radiation we're going to spend a lot of time on in a later unit. But the one we're most familiar with and the one that we're most reliant upon is the radiation from the sun. The sun is burning at average 6,000 Kelvin, which seems very high to us, which it is. And we're receiving those electromagnetic rays from the sun. And it turns out with electromagnetic radiation, if you heat up this horseshoe, for instance, it's glowing, right? And so it's at a certain temperature, it's glowing. And so we have that. We actually have that with different objects, at certain temperatures, they're sending out certain electromagnetic waves. And so, infrared, we're actually all shooting out infrared from our bodies right now. We all have a certain temperature. And if you had an infrared camera, you've probably seen those. If you want to do a quick Google or YouTube search, look up infrared camera, you'll see lots of examples where you can actually see what can't be seen. We know that the infrared electromagnetic rays are just before red. We can't see them with our visible eyes, or they're not visible light. We can't see them with our eyes. But if we have a special camera that can detect them, that will show us the different electromagnetic rays from that spectrum. So here's an example of taking a picture of a person. Based on the infrared coming from them, they have a certain temperature. When we also talk about light in terms of what's happening in this section, the absorption of light is very much dependent upon the substances here, right? So if you have light hitting this white surface, the snow, it's just going to reflect right back off, most of it. But when light hits this, when it hits the pavement or concrete, a lot of times it's absorbed, especially if you have asphalt. And so it's absorbed, that light's absorbed, and then it's also radiated out as well. And so a good absorber is also a good emitter. And when we talk about this, we talk about emissivity, and that's the number between 0 and 1 that gives a proportion of how effective it absorbs or radiates heat. And so coal is very close to 0. It absorbs absorbs light really well. It also sends out thermal energy really well. Metallic surfaces like this here are just going to reflect it. It's not going to absorb, or if you turn off all the lights, emit energy from it. So when we calculate that black body radiation, we can do that by multiplying the emissivity. And again, certain substances have much higher emissivity than others. We have the Stefan Boltzmann's constant here, and then we have the area that's exposed, and then we have the difference in temperature. The greater the difference in temperature between the substance and the outside, the greater the power, the greater how much energy or heat in a period of time that we're going to have coming out of it. And so in this first example that we're going to look at with the dog walking at night, their emissivity is 0.7, and the dog's temperature is 39 degrees Celsius. And in this case, we're going to figure out first what's the power output of this dog. And then, we can figure out the total amount of energy lost in 20 minutes. Now, as you set this up, and here's the dog, right? And we've got, we have to have our temperature in Kelvin, so you have to be careful with that. And then you're going to do the temperature calculation first. You're going to take the temperature in Kelvin of the dog, 39 plus the 273, and then take that to the 4th power. Then subtract the outside temperature, 2 degrees plus 273, take that to the 4th power before you do anything else. So why don't you go ahead and calculate the power output first, and then once you do that, we'll check that, and then we can do the second part. So go ahead and pause the clip and try that, and then when you're ready to check, you can hit play to continue. Okay, so we've got that. Our values, we should get, multiply those, we should get 96.92. Now what I want you to do is go ahead and try, in 20 minutes, how much energy does this dog lose? If this is the power output by the dog, thermal energy, how much energy is lost in 20 minutes. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right, so power is energy and time. 20 minutes would be 1,200 seconds. 96.92 watts is the power, And so the total amount of energy, 116,304 joules, would be how much energy this dog would lose in a 20-minute walk if that was the two temperatures.